Okay, in this lecture we're going to use what we've learned about discrete stochastic processes, specifically discrete master equations, to develop a classical nucleation theory. This is going to be following the work of Becker and Doring. But before we dive into that, let's just review some of the things that we know about phase equilibria for two-component systems. Okay, so if I start with a phase diagram, let's consider a case where we have components A and B. And so if I plot the fractional mole fraction of species B from 0 to 1, and on this axis I'm going to have temperature. Over here at 0 we have pure component A up and down this line. Over here at 1 we have pure component B. And I know that pure component A will have a melting point. So let's call that T sub m A. And I know that component B will have a melting point as well. Let's suppose that that's a little higher. So that's the melting point for component B. There is a region where I can go on this phase diagram slightly in from pure component A, where it will tolerate some impurities of species B. And likewise over here, there's a region where the B phase will tolerate some impurities of species A. Right across here is a boundary, and let me fill in some more of this. Okay, so up here are places where a mixture of A and B will be a liquid at high temperatures. Okay, so this is my liquid region up here. This is a eutectic point, liquidus. What's going to happen then, so let me fill in some places that I'm allowed to find materials in these regions. Okay, so these are all allowed regions of liquid composition at those temperatures, and allowed regions of an A phase composition and a B phase composition. Now, if I go to low enough temperatures, I just get an equilibrium between A and B in the solid state. At higher temperatures, I can get an equilibrium between a liquid and a solid. In this case, a solid with primarily composed of species B. But I can also do the same kind of thing over here. If I start from this point and this point, there are tie lines across there that will give me the composition of A that's in equilibrium with a molten liquid mixture. So now what we want to do in nucleation is to think about what happens when we start with a system, say here, and we quench to go down to a metastable condition. So no system is actually supposed to live in here, right? So if I prepare this system at that little circle shown there, then what happens is that it wants to phase separate into a B-rich portion and a liquid portion. But before it can do that, it has to nucleate this phase transition, right? So it has to create the first little embryo of the stable phase within the metastable liquid state that I prepared, right? So I take this thing's liquid and I instantaneously drop its temperature, and now it's sitting here as a metastable phase. It wants to give birth to a little solid B phase, but that's going to require a nucleation event, right? So let's talk a little bit about those nucleation processes. We're talking about a solute nucleus here. So basically, in order to count the size of that nucleus, we could just count the number of solute atoms that are involved. Okay, so we're going to use nucleus size as the progress coordinate for the nucleation process. And we're going to borrow from a model proposed by Gibbs to describe the free energy as a function of nucleus size. And I have a chemical potential driving force between the system that I start with, which is this metastable phase right here, and the systems that are going to be in equilibrium with each other. So those two will have the same chemical potential. But I can look at either of these two and then ask, well, what is the chemical potential of the system right here, and what's the chemical potential of the system right here? And that defines a thermodynamic driving force, a difference in chemical potentials, that I will then multiply by the size of the nucleus that I have. So I get an N delta mu, and by convention we usually make that delta mu positive, even though it probably really should be negative, but that requires then that we put a negative sign in this equation. That's not the whole story, right? This is the free energy in the bulk to grow a new phase of size N when the chemical potential driving force is of size delta mu. But we also have to create an interface between the new phase and the old phase. So that term looks like this. All right, so this is an interfacial free energy. This whole thing, A n to the 2/3, is like a area contribution, and so the A is a shape factor, and it depends on the shape of the nucleus. For example, if this thing is spherical nucleus, then that shape factor will be 4 pi times 3 times the volume per atom in the nucleus over 4 pi, all to the power 2/3. This is surface tension. When we multiply this shape factor by n to the 2/3, we get the area of a nucleus of this size n. Okay, so this is what allows us to think of this as an interfacial free energy term. This is energy per area multiplied by the area. Then we have a chemical potential driving force. That chemical potential driving force is kBT times the log of supersaturation. So let me write supersaturation like this, C over C sat. But the C over C sat is often just written as S. Okay, so this thing here is S, and it stands for supersaturation. All right, so this is a little bit of background information. But before we leave this, let me just draw the nucleation free energy barrier. We only really care about nuclei of size 1 or greater because we're talking about a solute precipitate nucleation process, so there's always at least one solute if I'm going to talk about a nucleus, and that barrier then is shaped like this typically. Rises sharply at the beginning, then falls off. Now this is a special place on this barrier. This is the critical nucleus size, somewhat like a chemical reaction transition state. So if I prepare a nucleus that's of size larger than the critical size, it will tend to go to the right. That is to say, it will tend to grow and continue to consume more of the metastable phase. If I prepare a nucleus on the left, it will tend to dissolve back into the metastable phase. This would be a precritical nucleus over here. Those tend to shrink. Postcritical nuclei tend to grow. All right, and critical nuclei are the ones right here at the boundary. You know, all of them will grow or shrink, but statistically, on average, they don't go anywhere. So n double dagger is the place where the derivative with respect to n of this free energy is equal to 0. So if I take this free energy and I differentiate it with respect to n, and then I set the result equal to 0, and then I go through and I solve for the value of n, then we get that n double dagger is equal to 2 times gamma times a divided by 3 delta mu, and all of this gets cubed. All right, so there's a few predictions buried in here. So the shape factor matters, the interfacial free energy matters, and those things both tend to drive the critical nucleus size up. The chemical potential driving force matters, but as the chemical potential driving force increases, the critical nucleus size gets smaller and smaller. And we showed this in our chemical equilibrium lectures, that we can relate this free energy profile to the equilibrium concentrations of nuclei of different sizes. So this is what we mean by that. That if I could prepare a system in which nuclei of all sizes were at equilibrium with each other, then the free energy as a function of n minus the free energy as a function of n evaluated at 1 would be minus kBT log of the concentration of n mers at equilibrium divided by the concentration of 1 mers at equilibrium. Now, of course, you can check this and make sure that it's self-consistent, and it is. So if I put in n equals 1, this term becomes 1, the log vanishes, and indeed that left-hand side also goes to 0. Okay, so that gives us some physical interpretation for the meaning of the free energy profile that we talked about over here in terms of this hypothetical equilibrium between cluster sizes. Now what we want to do is to use that critical size, evaluate the free energy barrier there, and of course that will become very important for determining how large the barrier is that has to be overcome to give birth to a nucleus that is post-critical and continue to grow.
Coronavirus.
Haven, go away. Okay, so that barrier is just plugging in the value of the n double dagger here into the free energy there, and then simplifying everything that we get. We get the free energy is going to be 4 times gamma A cubed divided by 27 delta mu squared. And it's convenient in many cases to go ahead and normalize this by kBT. Okay, so we can write beta F C and T. I have a beta. I have one extra factor of beta. I can use two of them here, but this gives me beta gamma A cubed, which is like a little surface energy normalized by kBt raised to the third power, divided by 27 times beta delta mu squared. And this now in the denominator looks like just the log of the supersaturation, because remember that this delta mu was kb times the log of S. When I multiply by beta, I get rid of the kBt, and we're just left with the log of S squared in the denominator. Okay, so this is the size of the nucleation barrier. Again, a lot of predictions buried in this little equation. You can see that the barrier goes up with the cube of the interfacial free energy, and it goes down with 1 over the squared log of the supersaturation. Okay, now the question is, how do we go from the barrier and the description of the thermodynamics of the free energies of clusters of different sizes to a description of the rate of nucleation? And that's a non-trivial step. We're going to keep this page handy, and when I need it, I will refer back to it. Okay, so page 2 of our derivation is really the parts that are found in the Becker-Doring analysis in 1935. And the basic idea here is that the nucleus grows one attachment or detachment event at a time. Single monomers come and they attach to a nucleus of size n to make a nucleus of size n plus 1. Monomers can detach from a nucleus of size n to make a nucleus of size n minus 1. And so now the states in my master equation are going to be state for size 1, 2, 3, 4, all the way out to infinity, and we're going to need transition rates. These are going to be rate constants for the attachment to a nucleus of size n. We'll call that k sub n, and we're going to use that notation throughout. So attachment to a nucleus of size n minus 1 is kn minus 1. We're going to have detachment events from a nucleus of size n plus 1, and we'll call that k sub n plus 1 with a minus sign to indicate that it's a detachment step. There are a couple of constraints on these rate constants. We already know what the free energy profile looks like between each of these steps, and we know that it's related to the concentration of nuclei of different sizes at equilibrium if we could prepare that system. It's a hypothetical equilibrium because the chemical potential is driving the system towards nuclei of infinitely large size. The forward and backward rate constants now, they must obey detailed balance. And pay attention to how we're using detailed balance here. We're not using it at equilibrium. We're saying that we know the equilibrium properties of these nuclei. We can use them to enforce a relationship on the forward and backward rate constants that we will then use even when the system is out of equilibrium. Okay, so let's see how that works in practice. Between a state n plus 1 that can lose a nucleus, we have an equilibrium concentration, and it must be equal to the rate at which the equilibrium concentration of nuclei at size n gain monomers. Okay, so this is now a constraint that relates for any n, the kn and the kn plus 1 minus. Okay, so what this allows us to do is to eliminate all of these constants. Okay, so you can see here that there's just a little bit of algebra left then to take this detailed balance expression and eliminate each of the kn minus rate constants in favor of the forward rate constants and a ratio of equilibrium concentrations of nuclei of different sizes. And of course, this can then be written in terms of that free energy model of Gibbs with the bulk and the interfacial contributions. Now what we're going to do is we're going to construct the master equation. And instead of trying to write down a matrix, we'll just keep track of the 4 terms that are involved at every state, right? So we have an attachment from nuclei smaller than n, generating nuclei of size n. We have detachment from nuclei of size n, removing them. We have attachment at size n that removes nuclei of size n, and we have detachment from nuclei larger than n. What we're going to do is something that we haven't seen yet in the class thus far, and that's to impose these rescue and replace conditions. Yeah.
What's that?
Well, I'm on film, and now you're on film too.
Hi.
Okay. All right, so the rescue and replace conditions are a steady state construct where we imagine that there's some daemon that can grab large nuclei as they form, dissolve them, and replace them back into the solution. And what we're going to get then is a steady state flux. We're going to have a slow leak from a quasi-equilibrated population of small nuclei occasionally generates large enough fluctuations to generate post-critical nuclei, but post-critical nuclei will grow over the barrier and be grabbed by this demon, redissolved, and put back in, and we can then count the steady state occurrences of these nucleation events. And that's going to be our nucleation rate. It sounds a little crazy, but think about the way a crystallizer works. You have a well-stirred medium, nuclei are generated in the bulk, and they grow, but if they live in the crystallizer long enough, they will eventually go through the outflow, and more solutes are being pumped in all the time to replace them, and it's a steady state process just like the one that we're describing here. Okay, if we're going to compute the rate at steady state under these rescue and replace boundary conditions, then we can take any intermediate value of n, and we can cut the chain of states in between them and count the net flux this way minus that way, and equate that to the nucleation rate. So our steady state rate is the forward rate at state n minus the backward rate. Okay, and I want you to notice that we did not use equilibrium populations here. We used the steady state populations here, and we don't know them yet. But what we're going to do is to factor out the equilibrium populations and write the steady state populations as a ratio of the steady state to the equilibrium. So I'm going to factor out CEQ of n, the equilibrium concentration of n-mers, times the forward rate constant, and I'm going to leave behind now a function phi of n minus a phi steady state of n plus 1. All right, so let's see what this function phi has to be in order to make this a valid equation. So it has to be the concentration at steady state of n-mers divided by the concentration at equilibrium of n-mers. Now, it may take some scratching your head and going back and checking this, but basically what we've done now is we wrote our steady state flux in terms of equilibrium probabilities and transition rates multiplied by the difference of this phi function. And phi is telling you about the ratio of steady state to equilibrium population. This is somewhat like fixed law if you look at this expression. If you look at this expression, it's a little bit like this. We have a flux is a rate constant multiplied by a derivative of the steady state concentration with respect to n. Now these things are giving me this derivative of the steady state concentration. The fact that we're subtracting the n plus 1 from the n instead of the opposite is why we have a negative sign here. And we of course are writing this steady state concentration as a equilibrium probability multiplied by that difference in the steady state phi values. Now what about the boundary conditions? Okay, this is where our rescue and replace boundary conditions come in. We're going to require that at equilibrium we just have that the steady state concentration of 1 mers is the equilibrium concentration of 1 mers. Now we don't really have a well-defined equilibrium concentration of 1 mers, especially at conditions where everything should be converted into things of infinite size. But we can always talk about ratios of equilibrium concentrations, and we're not going to have any infinitely large nuclei because of this Maxwell's demon that's pulling them out. So we're going to let that ratio, phi SS at 1, just be equal to 1. Now at infinity, we are removing all the large nuclei, and so the concentration at the ratio at steady state should go to 0. Equilibrium would like it to diverge and become infinitely large, and at steady state we're going to have something very small. So it's very easy for this limit to go to 0. Okay, so this is going to give us a quasi-equilibrium description, is right here, and this is our steady state rescue and replace boundary condition. Okay, now we get to do my favorite part of this derivation. So if you look at this equation, we cut this at an arbitrary place, and so this equation for J is true regardless of which place we had cut it. And that means that now we can write all of these things and add them up. So we could write this way, phi SS of 1 minus phi SS of 2, and solve for this difference. And we would get J, so we're just basically rearranging this equation for a specific example of n and solving for the difference of the two phi's. So this one comes out to be J divided by the concentration at equilibrium of 1 mers times the rate of attachment to a 1 mer. Now if we do phi SS of 2 mers minus phi SS of 3 mers, then we get J over CEQ of 2 times the rate of attachment at a dimer. And we can keep on going with these equations. Each time we get a term that looks like this. Okay, and we keep on going down. Okay, so what I'm going to do now is add all of these things up. And now, what's going to happen if I add all of these? I have a phi SS of 2 with a minus sign and a phi SS of 2 with a plus sign. So these two terms are going to cancel. And these two terms are going to cancel. And we continue on down this way, all the way till we get to infinity, and we end up with phi SS of 1, and that's the only term that's left, because we know that these things are getting small, and in the limit they're going to 0. So the only term that's left on the left-hand side is phi SS of 1, and we have summed all of these things from n equals 1 to infinity on the right, and each term has the form of j. There's only one nucleation rate, regardless of where we cut the series, and each one has a denominator term of CEQ of n multiplied by the rate of attachment at an enmer, and so that is my expression. Now, I know from my boundary condition that phi SS of 1 was just equal to 1. Okay, and now you see that we have an equation that we can solve for j right here. All right? Okay, and now what we can do is we can take this equation down here that we just derived, and we can solve for the nucleation rate. Okay, so we get that j...
The screen.
Oh, thank you. My assistant tells me that I'm off the screen. Thank you, Lyndon. All right, so I can solve for j, and the value of j ends up being the sum up to infinity of n equals 1 over CEQ of n, k sub n, and this is a series that I'm adding. And when I solve for j, I end up having to take the sum of all those terms and putting them to the minus 1. Okay, so all we did was factor out a j from this equation and then solve for the j. Okay, so this means, so this is called the Becker-Doring equation. And you'll spot this all over the place when you have one of these problems where you have a bottleneck in a long series of transitions and a continuous steady state flux through that bottleneck. So you can do very similar derivations for all different kinds of problems. For example, 1D nucleation, fibril elongation, things like that often have this kind of solution. So why is this significant, and where and what does it really mean? Okay, well, remember that the free energy landscape, F, C, and T, looked like this as a function of n. If we plot it with our reference state being 1, then we get all these different values of n that go up like this and then go back down. Now, the free energy is the negative logarithm of the equilibrium concentrations. So when the free energy is very large, very high, the equilibrium concentration becomes very small. And you have this very small term in the denominator that makes the 1 over that term be very large. And so the effect of that is that what you learn from the Becker-Doring analysis is that the entire rate is dominated by fluxes up here in the neighborhood of the top of this barrier. Right? So the rates depend on the kns and the free energies at states near n double dagger. And for all practical purposes, you really only need to know the shape of the energy landscape right here in the neighborhood of the top of this barrier. So much like transition state theory in a way, except that we do have contributions from points that aren't exactly here. Now we have contributions that are decaying in importance as you move away from the top of the barrier. And hopefully that's let me mark this down for completeness here, that this is our critical nucleus size. And the Becker-Doring analysis tells you how to compute the rate using the equilibrium properties, attachments, and free energies at every one of these states. Now, it is somewhat of a complicated formula, and it's a little bit difficult to extract simple trends out of this because all of those free energies are wrapped up in this infinite series of equilibrium concentrations and kinetic factors, but there is a way that we will learn in a couple of lectures to turn this master equation for a set of discrete hops between neighboring states into something called a Fokker-Planck equation. And when you do that, you get an extremely simple version of this rate expression. This Becker-Doring equation becomes something that's actually extremely simple then, and much more practical for making predictions about trends in nucleation rates. And that's it.
Goodbye.
Lyndon.